And so what I want to talk about, a little bit about my specialty in terms of the potential of organic waste, and my experience is focusing a lot on the agricultural side. Clarkson is a very rural community, and so we live in a county where we have plenty more cows than we have people living. And so we can talk about agricultural waste quite a bit. But we also, I was participating in a class last semester, and some of the issues we had talked about, students had to think about is in terms of water cycle and wastewater. And Dominic already addressed some of those aspects, saying that essentially we're producing a lot of, per person, we're producing a lot of wastewater. So just looking at Montreal, if there's in a metropolitan area, we're producing about 1.3 million cubic meters per day, or 350 million gallons per day in wastewater, which produces a lot of solid waste. And so that's a lot of organics which could be used some way. Similarly, when we look at solid waste generation in Quebec or in Canada, we're producing a lot of organic waste or just regular waste. So 1,700 pounds per day, per year, per person at municipal waste. It's a large industry, what already was stated earlier. So we're talking about $1.3 billion in municipal waste, solid waste management costs. And when you look at the materials in Montreal, so this is a slide, I'm not sure whether you can see this. When you look at a split of solid waste in Montreal, about 50% is organic solid waste in a residential area. Only 8% at this point is recovered, recycled. Most of the other part is waste, ends up in landfills. Recycled materials like paper and other materials are more recycled, 40%, but again, it's not, there's a lot of potential in terms of recycling or recovering essential resources from that solid waste stream. To address that, so there's a proposal that anaerobic digestion, so this is the blue circles right here, so in the area in Montreal, there's potentially siting of anaerobic digesters to ultimately address food waste, which is generated in these areas, and then composting facilities, which ultimately will collect that solid waste in order to meet these municipal goals to recycle materials. Well, when you look at anaerobic digestion in general, that recovers, obviously, carbon. The carbon can be converted to energy, and we can ultimately retain some nutrients in the digestate. The composting retains the carbon, nutrients, all in that material which we ultimately produce. And both processes reduce significant pathogens, which could also be of interest. So when we look at installed capacity, biogas capacity, and to look at a global impact, I just found that slide, which ultimately shows that overall, Germany last year, for example, generated about 5,000, has a capacity of 5,000 megawatts of capacity in biogas plants. So they're the leader in biogas plants. Others, US is following, and then other countries are following. So that's overall, in the overall electricity market, is a pretty small amount of electricity generated. But yet it could be significant in a local economy. So when you look at Germany, the growth in Germany, the biogas plants, had a significant increase in electricity generation over the last 10 years. So you can see this went from 1.4, so almost a 20-fold increase over in electricity production. So it's a significant increase, and the increase is really driven mainly by, not surprisingly, energy prices. And I can show you this in a second. The way these systems work, they're using essentially energy crops, so farmers grow crops, and then there's bio-waste, so this is animal waste, and a very small section is really only the municipal waste, or the food waste production. So these are energy crops, and then ultimately this is the animal waste. So these are farm systems generating most of the capacity. When you look at prices in electricity, just as a comparison, Montreal, so this is from Hydro-Quebec for residential areas, in Canadian dollars, you're paying about 7 cents a kilowatt hour. United States, we're paying more than, not surprisingly, in Quebec. And when we compare that to Germany, converting it in Canadian dollars, that's paying about 44 cents a kilowatt hour in Canadian. So significantly more, obviously, than in Montreal or in Quebec. So that is really the main reason, in addition to Germany had very high feed-in tariffs, so this is, maybe you can see that very well, had high feed-in tariffs, so where the utility also paid a surcharge for ultimately generating electricity into the grid, to the suppliers. So that's obviously a big revenue, and that explains the significant increase in biogas production facilities in Germany. Okay, so when you look at that, so if electricity is cheap in Montreal, so what other sources could we use? That essentially explains why Canada doesn't show up in that slide, right? It has very few digester facilities, and very few in Canada. So if electricity is not the driver, what else can we use to ultimately make use of that resource, that carbon high energy resource? And so there was a study done which then looked at other capacities, and I think even the urban digester facilities in Europe, they make use of, for example, heat, right? So heat is certainly an area where digesters could help, or anaerobic technology could help significantly. Others increased in capacity, CHP capacity, so combined heat and power capacity, again, because electricity prices are high in Europe. So in our case, so this heating is used mainly for residential use or for district heating in Europe. So that would be one possibility of using the energy generated other than electricity generation in a typical biogas plant, a digester plant. I want to show you a couple examples which we have done in northern New York, just to give you some other potential resources which we can recover from anaerobic digestion. And so the one I've been involved in, this is a large facility in northern New York where that facility has electricity prices of 2 cents a kilowatt hour. So through economic development, they get actually very low electricity prices, yet they were interested in installing a digester, and not because of electricity generation, but mainly because they are using, in addition to electricity generation, they could use the solids removal. Here we go. So they have a digester, and they're ultimately removing solids. The solids are used for bedding, and I'm going to explain this in a little bit more in detail. So electricity, they're producing about 500 kilowatts in power, but yet which they can share among several of their farms, so through net metering arrangements, but then they are using the bedding also for the animal feeding, and that makes the system economical. So for those of you who might not know too much about large-scale farming, so large-scale farms, dairy farms, they use essentially these freestall barns, and freestall barns use, the cows can move freely in areas, and they ultimately are placed on, or they can lay down on a bedding material. That bedding material, the more comfortable the cow is, the more milk produced, the more the cow likes to sit down, lay down, and the less energy it produces by wastes by walking around, but by producing milk. So the farmer is always concerned about a very comfortable bedding material, because which ultimately allows the cow to produce the maximum amount of milk. That bedding material needs to be clean, because if the cow gets sick, they can't sell the milk, right? So so pathogen content is very important for that bedding material, because that could potentially be an infection for cows. And so what these large-scale dairies at this point potentially use bedding materials like sand, which is inert, and it ultimately has very little ability to essentially host pathogens, right? And but it has a lot of concerns in terms of materials handling because it's very abrasive. Right? But some farmers really like sand because it's very comfortable. Sawdust is another very common bedding material, but it's now the price of sawdust gets high because of competing markets in terms of pellet manufacturing. So the price is very high for those farmers. And so more common is now that farmers use recycled solids or manure solids, and they can be either composted or digested to reduce the pathogen content. And so that's farm we worked with are using that process. And so so that solids is ultimately, so this the center picture is a large-scale digester. This is the digester in operation. The green tower is a biogas cleanup system for sulfur removal, and then there's the 450 kilowatt engine, combined heat and power system engine, and up here is the recovered solids. So after the digestion, the material goes through the digester for 30 days. It would be separated through a screw press material, and this is the material that comes out. And that's the material the cows will ultimately be bedded on, be laying down on. When you look at the economics, straight economics, there's a lot of numbers, but the one I want to focus on is really, so this is about a $3 million project, capital cost project. The farmer earns yearly, or essentially replaces about $110,000 worth of electricity costs. Even at that low electricity, that's the savings he has. But in bedding, he saves about $330,000. So when you take those both numbers together, the payback period of that process was about 7 years. So it's even so electricity prices are low, that just because you have the market of replacing organic materials becomes a very economical design project. And it's very simple in that regard. I want to give another example of a small, very small food digester system. So talking about waste management system in a very small town. North Elba is actually is located in Lake Placid, so where the Olympics were in 1980, so a long time ago. So it's a progressive mountain town who want to ultimately recover the, essentially reduce waste disposal fees and make some money in the little village. And so that system is very small. It only treats about 1,000 tons of food waste per year. Again, that town has economic development funds, so electricity is really not an issue. They're paying about 3 or 4 cents or 5 cents a kilowatt hour. So it's not the driver. The electricity pricing is a minor driver of that process. So this is a system which comes essentially in a containerized system. And when you look at the economics, so the numbers are very small. So the electricity generation is about $15,000 a year, so it's a very small system. But what they ultimately make money off is the tipping fees, right? So the tipping fees, disposal fee of collecting the organic waste, that's the money making system. And even that system at the small scale becomes cost effective. It becomes cost effective predominantly because the town has funding from the state to ultimately install this. So the capital cost is ultimately paid for through a development grant. If it didn't have that grant, then the payback period for that little tiny system would be very long, right? But both of those systems illustrate that you can use, so electricity is not the necessary driver, but the driver in this case are the management practice, so the solids removal, or ultimately the solids recovery for the particular business. So another example, what we have done in our labs is we are extending, when we're taking food waste, we're looking at the impact of inhibition. So it's well established that, for example, ammonia is very inhibitory at high concentrations for that process. And so what we've been working on is to remove ammonia during digestion. And the typical way to remove ammonia is to strip it and bring it back into air in form of nitrogen gas. we think we can ultimately recover the ammonia and have another resource available as a fertilizer. Rather than putting it in the air, we don't have to make essentially ammonia gas again, ammonia fertilizer, we can ultimately recover that ammonia. And we do that by using essentially an ion exchange membrane, and that has an additional benefit of where we putting into the digester potassium. And so when we look at the balance of nitrogen, phosphorus, and potassium as a effluent from the digester in terms of fertilizer value, when we're just treating food waste alone, it's imbalanced. It's not a very good fertilizer. We have way too much ammonia, and we don't really have much potassium. And so we can now control the fertilizer value and control the ammonia concentration, reduce the ammonia concentration, which then allows us to ultimately produce more biogas. So we produce more energy, but we also produce a better effluent, which then becomes a better fertilizer value. So just to give you an example, so when we have the membrane system, this is biogas production as a function of time. In a batch system, we're producing, when we're reducing the ammonia concentration from 7,000 milligrams per liter to 4,000 milligrams per liter, we produced about 75% more biogas, methane, in that membrane system. When we reduced the ammonia concentration from 55 to 2,400, we had less of an impact. And that's because when we look at this inhibition curve right down here, at lower concentrations or at some concentrations, the impact of removing ammonia becomes not very cost effective. But down here it is very significant at high concentrations. So what that shows us is that now in that process we have, again, like I said, we have a control, we have a method to increasing biogas production or methane production. We have a potential to balance the fertilizer value of our effluent, which increases value, and then ultimately we can, the recovered ammonia on its own through the membrane system, we can also use that for other needs as economic growth. So all three things together will make that process more economical for food waste, for a specific waste category. So in summary, so I showed that, presented you some data where we have some large amounts of organic material is produced in local areas, in just looking even at in urban areas and agricultural areas. Because of the lower cost electricity environment like in Montreal or in Quebec, the focus really needs to be on resource recovery, on other ways to ultimately to recover other means than just looking focus solely on electricity. All those resources, especially when we look at the resource needs, so what we use these resources for, are temporary and spatial dependent. So it doesn't pay to truck manure or organic waste for very long distances because it's very, so that's very costly. So the best solutions are local solutions where we have less transportation costs, where we meet resource needs and resource availability. And I think that's really needs to be the key in terms of looking at coming up with resource recovery processes. So, all right.